In the infinite repository of the cosmos, there are ideas that possess a strange allure, crossing the boundary of science to touch the deepest realms of human imagination. Perhaps no idea is more sparkling and enchanting than the image of a diamond planet, a colossal, brilliant sphere floating in space where mountains and valleys are carved from the hardest and most precious material we have ever known. It sounds like the setting for a grand science fiction epic, but the astonishing thing is this idea is not merely a product of fantasy. It was born from cold, hard data, from complex mathematical equations, and from a chain of elegant logical reasoning by astronomers. The story of the diamond planet, particularly of a prime candidate named 55 Cancri E, is a powerful testament to how the reality of the universe can sometimes be stranger and more incredible than anything we could invent. This is not a fairy tale. This is a scientific detective story. Together, we will follow the faint clues recorded by telescopes millions of kilometers away, decode the language of light and gravity, and build a portrait of an alien world, a world of unimaginable pressure and scorching temperatures. And through this journey, we will see the true beauty of science, not in providing final answers, but in the relentless process of asking questions, building hypotheses, and being ready to overturn what we once believed to be true. The search for planets outside our solar system, or exoplanets, is a formidable challenge, as they are too small, too dim, and too far away to be photographed directly. Astronomers have developed incredibly clever indirect methods, turning them into brilliant cosmic detectives. One of the most effective tools is the transit method, which relies on observing the minuscule dimming of a distant star. When a planet passes in front of its parent star from our point of view, it blocks a tiny fraction of the light, creating a small, regular dip in the star's brightness curve. This dip tells us the planet's size and its orbital period. Another crucial method is the radial velocity method, which observes the wobble of a star caused by the gravitational pull of an orbiting planet. This wobble causes infinitesimal shifts in the star's light spectrum, allowing scientists to detect the planet's presence and calculate its mass. When we have both the size and the mass, we can calculate a critically important parameter, the planet's density. Density is the first and most vital clue to speculating what a planet is made of. In 2004, astronomers discovered a new planet orbiting the star 55 Cancri A, about 41 light-years away, and named it 55 Cancri E. A few years later, they confirmed that this planet also transits its star. For the first time, we had both its mass and its size. The numbers were staggering. 55 Cancri E is about twice the diameter of Earth but nearly 8 times more massive, making it a super-dense super-Earth. But the most shocking fact was its orbit. A year on this planet lasts only 18 hours. A giant super-dense, super-hot world spinning at a dizzying speed. The investigation began. How did scientists leap from dry numbers about density to a glittering hypothesis of a diamond planet? The clue lay in the parent star. Planets are born from the same massive disk of dust and gas that orbits a young star, so their chemical composition reflects that of their star. Using spectroscopy, astronomers can analyze a star's light to determine its precise chemical makeup. When they analyzed 55 Cancri A, they found something unusual. It is a carbon-rich star with a significantly higher carbon-to-oxygen ratio than our own sun.
This was the missing piece. A carbon-rich star means a carbon-rich planetary system. In such an environment, planet formation would proceed very differently. Instead of having a crust and mantle composed mainly of silicate minerals like Earth, a planet like 55 Cancri E would likely have a thick crust of graphite. Beneath that crust, deep in the mantle of a planet 8 times the mass of Earth, the pressure and temperature would reach unimaginable levels. Under such extreme conditions, carbon exists in its most stable form, diamond. Theoretical models suggested that a third of 55 Cancri E's mass, equivalent to 3 times the mass of the Earth, could be a gigantic solid layer of diamond. The picture was complete. A planet with an iron core enveloped by a diamond mantle thousands of kilometers thick. The diamond planet hypothesis was born. The image of a sparkling diamond planet evokes romantic notions, but the scientific reality paints a picture of a true hellscape. Being so close to its parent star, 55 Cancri E is almost certainly tidally locked, meaning one side of the planet perpetually faces its star while the other is cloaked in eternal darkness. The day side is a fiery inferno, with surface temperatures potentially reaching 2,400 degrees Celsius, hot enough to melt rock and create boiling oceans of lava where it might rain molten glass. The night side, though dark, is far from cold, with temperatures still potentially reaching 1100 degrees Celsius. This might be where mountains of graphite and valleys of diamond exist. Any atmosphere on this planet would be a toxic brew, possibly filled with hydrogen cyanide. It is not a treasure. It is a cosmic furnace. Science is not a collection of static facts, but a vibrant dialogue between hypothesis and evidence. The diamond planet theory, though compelling, has not stood still. New observations from space telescopes like Spitzer and Hubble have begun to paint different, sometimes even stranger pictures. The planet's thermal map showed that its hottest point was not directly facing the star, suggesting a very thick, circulating atmosphere with supersonic winds carrying heat around the planet. Some scientists have proposed a completely different scenario, that 55 Cancri E could be a giant water world, where water exists in a bizarre state known as a supercritical fluid with no clear distinction between liquid and gas. A third hypothesis, based on the detection of hydrogen and helium in its atmosphere, suggests it might be a mini Neptune, a planet with a small rock ice core enveloped in an extremely thick hydrogen-helium atmosphere. So is 55 Cancri E a diamond planet, a water world, or a mini Neptune? The current answer is, we are not certain. This does not make the story less compelling. On the contrary, it makes it more authentic. It shows how science works. A beautiful hypothesis is proposed, then new evidence emerges, forcing us to reconsider, refine, and build new, better theories. This is not failure. This is progress. The diamond planet hypothesis, even if not entirely correct, played a crucial role in forcing scientists to think creatively about the diversity of worlds beyond our solar system. The journey to understand 55 Cancri E is a story about the nature of science itself. We began with a fairy tale idea, followed scientific clues to build a logical hypothesis, and then continued the journey, confronting new and challenging evidence, willing to open our minds to new possibilities. Even if 55 Cancri E is not a diamond planet, the value of that idea remains. It has ignited the curiosity of millions and pushed the boundaries of our understanding of the universe a little further. The cosmos has no obligation to meet our expectations. It is more complex, diverse, and surprising than we can imagine. Ultimately, the real treasure is not a planet made of diamond. The real treasure is the journey of discovery itself, the beauty of asking questions, of reasoning, of observing, and of relentlessly seeking. In this vast and largely unknown universe, that is perhaps the noblest role of humankind.